All right. So last time we were looking at, or we had finished up with section 1.5 or 1.4, right? Sounds right. So I'll start with questions from homework. I don't think we assigned anything new from last time. I think we're just up through like 1 through 18 or whatnot. But if anybody has any new questions on that stuff after having to make sure your problem set was finished up over the weekend, we can certainly deal with that stuff. Okay then, very good. Today then we're going to do sections 1.5 and 1.6 is the plan. So in section 1.5, we're going to talk about symmetry. So again, in chapter 1, we start off talking about functions and like what a function was, right? Now we're going to, and we've transitioned now into talking about like attributes of functions, ways we can describe like what a function might look like or how it might behave. We're going to continue that. Symmetry is another descriptor that we can use for functions. So there's 3 major types of symmetry that we're going to talk about in this class. The first kind is symmetry with respect to the x-axis. And WRT is an abbreviation for with respect to. So I'm just abbreviating those 3 words as WRT. So let's draw a little, or let's look at an example of a function that has this type of symmetry. What's up? No. So I'll draw, or we'll write down an equation that represents a function with this symmetry. We'll draw a graph of a function that represents or that has this same symmetry, and we'll do an XY table and just kind of look at the different ways we might represent the function and talk about what we're looking at to see that it has that type of symmetry. So let's look at the function x is equal to y squared. Well, I shouldn't say function. The equation x is equal to y squared. This is an example of an equation, or an equation that has symmetry with respect to the y-axis. Now, looking at this, not very meaningful to us, right? It's tough to even look at an equation and tell this a symmetry that might be going on just by looking at it. What we could do, though, is we could translate this into a form that we could graph. For example, using our calculator to do that, right? If I wanted to graph this on my calculator, can I graph it in the form that it's written? No. Good. Why not? The y squared, right? So to be able to graph it, we need to get that y by itself. So we'd square root both sides. Good. So we would write that, right? Is that correct? Look carefully. Ah, there you go. Remember, when we square root both sides of an equation, that generates a plus or minus. Okay. So if we then chose to graph this, I'm just going to sketch the picture rather than taking my calculator out to do it. Mostly because we've graphed this thing before, I think in a previous section. Oops. So that's kind of what your graph is going to look like. Notice if you treat like the x-axis as like a mirror, and you like take a point here and you fold it over the x-axis, it's going to land on the other part of the curve, right? So the x-axis kind of divides it in half. Everybody kind of see that? So what we should be noticing is that if this is the point, we'll just say f comma f of x, then this point down here would have to be f or x comma negative f of x, right? Or it's the same x coordinate, but the y coordinates are opposite, right? So the table that we might see let's say we have 0 and 0, but for x equals 1, we'd have negative 1 and positive 1 as y's, right? If x was 4, we'd have negative 2 and positive 2 for y's. If x was 9, we'd have 3 or negative 3 and positive 3 for y's. Is everybody okay with me doing like a double column or like two values in the y column for this situation? Since for every x other than 0, we're getting a positive y coordinate and a negative y coordinate for that x, just like we drew our picture here above. So what we'd say here is that f of x should equal negative f of x. Right? If I take this y coordinate and negate it, I get another y coordinate on my function. Or if I start with this y coordinate and negate it, I get another y coordinate on my function, right? Does that feel okay? That's the opposite. That's the behavior that we're seeing. Let's look at the next type of symmetry. Here we are symmetric about the x. What do you suppose the next one is? Nobody with any intuition there? Yeah. So here we're going to have symmetry with respect to the y-axis. Now, this type of symmetry has a special name. We call functions with this symmetry, we call those even functions. So we most commonly use that term to describe a function that has symmetry with respect to the y-axis. We call those even functions. Why do you suppose we choose to do that? It's a lot less words, right? Mathematicians are inherently lazy. I prefer to call it efficient. And we'll use one word to replace, a whole sentence anytime we can. All right, let's look at an example. We'll do the same thing. We'll write an equation like f of x equals x squared. Now that's a form that we can just graph straight away, right? We remember from previously that f of x and y equals can kind of be used interchangeably. They basically mean the same thing. The only difference is that f of x notation gives me a little bit more information about what's the independent and dependent variables. But for the most part, it doesn't really give me any, they mean the same thing. So this one is going to look kind of like this. It's a little bit better, I guess. So on this one, if we pretend, say, the y-axis is our mirror, and I take some point on one side of it, and I kind of reflect it to the other side, this would need to be the point negative x comma f of x. Everybody's okay there? So what would my, if I made an XY table out of this, what would this look like? Well, I would notice that on either side, like 3 and negative 3, both give the same y-coordinate. As for each y-coordinate on like the right side of my function, there's a matching y-coordinate on the left side of my function. Everywhere except at wherever it's hitting the y-axis at, like that point of that plane of reflection, or that line of reflection, I should say. So what is my observation here? Is that if I evaluate negative x, should give me the same thing as evaluating positive x, right? F of 3 was 9, and f of negative 3 was also 9. They both give me the same y-coordinate. So this was about what kind of functions? Even was the name we gave these. Even functions have this symmetry with respect to the y-axis. All right. Our next situation is called 180-degree point symmetry with respect to the origin. Woof, Mr. Kulik, that is a mouthful. Yeah, you know what? This also gets a nickname. Functions with this type of symmetry we just call odd functions. That's a heck of a lot easier to say than 180-degree point symmetry with respect to the origin, which is like, just rolls off the tongue. Not really, guys. I'm being sarcastic here. odd is way easier to say than the alternative. So again, this gets a nickname. All right. Again, let's go ahead and look at some examples. If I look at the equation, f of x equals x cubed, this is an example of an odd function. If I went to graph this, the graph of this is going to look like kind of like that. So the idea here is if, say, I pick a point on my function and I build an anchor here at the origin and I like tie a rope to that point and then I spin that point like 180 degrees, which is just a straight line, right? You remember that from geometry? We end up with another point on our function. So that's why we call it 180 degree point symmetry with respect to the origin. Is the origin's like our point of rotation, that's where we're pivoting from, and then we're just spinning 180 degrees. Does it matter if I spin to the left or the right if I'm spinning 180 degrees? No, because they're just half a rotation, forward or backwards, ends up at the same spot. So if this is the point x comma f of x over here, this point down here, well, the x is negative because we're in the third quadrant, and the y is negative because we're in the third quadrant. Now, the other way you could think about this, instead of thinking about it as a rotation, you could just think about it as like a reflection across the y, and then also a reflection across the x, right? So like it would move it, like here and then down to there. You can think about it that way as well. And it doesn't matter if you reflect across the y first and then the x, or the x first and then the y. You both end up at the same spot, right? I think in geometry, when you talk about transformations, this comes up, but that was like 2 years ago, and it was like one section of a chapter that you probably don't remember that well. So if you're like, if you say so, Mr. Kulik, that's okay. All right, let's look at what an XY table for this would look like. So again, what we should notice here is that, like, for each y coordinate, the opposite x gives me the opposite y, right? 1 gives me 1, but -1 gives me -1. 2 gives me 8, but -2 gave me -8. 3 gives me 27, but -3 gives me -27. So my observation here is that f of -x should be negative f of x. That if I plug in like -3, I should be getting the negative of the y coordinate at 3, which is what I see, right? All right. let's do some actual examples. And I'm going to add in a little bit of instructions here. So we're going to determine whether the functions are odd, even, or neither, and then prove that. So we're going to add in a little bit of extra instruction. So the question is, first, let's figure out how to determine whether these things are odd or even or neither. What do you think is going to be the easiest way to do this? I would graph and look at the picture. The exponents aren't going to tell you the whole story. We can talk about what your observation is and where it falls down, and then what the actual answer is, but the exponents alone are not going to be quite enough. But that's okay. It's a good observation to start with. So I'm going to just graph x to the fourth plus 1. And now I've been using my calculator for all these different classes, so I'm sure my window's all screwed up. So I'm going to do zoom standard. I don't remember what the last thing I graphed on here was, but I'm guessing it was something that I'd zoomed in considerably to look at, because it looked like a calculus problem. All right, so if I look at this, odd, even, or neither, which one does this picture look like? Even, right? Because it looks like you're just a reflection across the y-axis. Looks like the y-axis is splitting the thing exactly in half. So far, so good? Will, are you scratching or are you questioning? Okay. So, looks even. All right. How do we do the proof for this then? Well, what we want to show is this, our observation from before, that f of negative x is equal to f of x. That's what we need to show. If we can do that for our function here, we're done. Everybody's okay? WTS just stands for want to show. So that's just me reminding myself what it is I'm trying to get in order to accomplish this proof, for me to be done. So when I have something I'm trying to prove that has an equality in it, typically the easiest way to start is to start on the left-hand side and try to end up with the right-hand side. So that's what we're going to do. So we're going to start with f of negative x. What does it mean, or what should I do when I have like f of negative x? What is that telling me to do? It doesn't mean to make x negative. Close. If I had instead, let's just treat this as an aside since the answer doesn't seem obvious. What if I had f of negative 2? What would I do with that? If there's just a number in there. What does it mean when I have a number in parentheses next to a function like that? Great, we're going to plug negative 2 in for the x's, right? So I would write like that. Everybody agree? What do you think I'm going to do for f of negative x? Plug negative x in for x, just like I did for the other one. Is everybody okay? Simple enough, right? Oh, it's like, oh, I should have said that. That's what I meant. I just said something that, sometimes you know, what's going on in your head and the words that come out in math talk don't always match, right? That's hard to do. That's one of the hardest things for students is to like, okay, I know what this looks like on my paper, but when I try to say it in words, I don't know how to say it, right? That's hard. Okay. Now what I want to do is I want to simplify this negative x to the fourth plus 1. Okay, so how do I do negative x to the fourth? What does negative x to the fourth mean? Negative x times negative x times negative x times negative x. Everybody agree with that? Because it's to the fourth power. And then I still have that plus 1 there. If I multiply 4 negatives together, what do I get? Positive. If I multiply 4 x's together, what do I get? Well, x to the fourth, right? So I have positive x to the fourth plus 1. Everybody feel good? And hey, wait a second. If I look at this, isn't f of x just x to the fourth plus 1? Isn't that what I have right here? So hold on, what have I just done? I started with f of negative x, and I've shown that that equals f of x. We are done. Yay! That completed the proof. Not too bad. Not bad at all. You just have to see it the right way. If you see what we're doing, and I'm trying to go through really nice and slow and deliberately so that it's easy to see what it is that we're doing. But when you see it, it's like, oh, this is not a big deal. All I do is like a little bit of simplification, and I know what I'm supposed to be getting because I looked at the graph already, so I know what has to happen. So it's not so bad. All right, let's look at part B. So again, let's graph g of x equals x cubed plus 3x. Two x cubed plus 3x. Let's hit graph. Looks odd to me too. Do we agree on that? Okay, so just like before, we'll start our proof by stating what it is that we want to show. If I go back and look under my odd function, the observation that we made, was that f of x, or f of negative x, equals negative f of x. So that's what we want to show. Now I'm actually going to, instead of use f's here, what letter am I actually going to use? I'm going to use g here because that's what the problem says. So I'm going to actually say these are g's. Let's not get confusing, right? Because we used a different letter in the problem. Let's try to be consistent, Mr. Gulick. All right. Yeah. Okay, so we'll start the same way. We're going to start with the left-hand side and try to end at the right-hand side, just like we did before. So just like before, to do g of negative x, I'm going to be plugging negative x in for x. So I'm still going to have the 2. In place of the x, I'm going to write negative x, and then I still have the cubed, and then I have plus, still have the 3, but in place of the x, I'm going to write negative x. So far, so good? Okay. Now let's simplify the expression here. So what is negative x to the third simplify to? Negative x to the third, right? Because we have 3 negative x's. 3 negatives make a negative. And then I have 3 times negative x. What does that simplify to? Right here. Negative 3x. Great. We feeling all okay? All right. What are we trying to end with again? Negative g of x. So now that I've simplified, what I'm going to do is factor off a negative because I know that I need to have that negative out front because I know that I want to end at negative g of x. So when I factor that negative sign off, negative 2x cubed becomes positive, and negative 3x becomes positive. Is everybody still doing okay? And look at this. What is this? That's g of x, isn't it? So I'm going to make a substitution here. I'm going to replace that positive 2x cubed plus 3x with g of x. Notice I still have that negative sign out front. And now what have I done? G of negative x equals negative g of x. That completes my proof. Yes? Because I want to have, look at what I'm trying to get to. I need a negative g of x. So I'm going to, no matter what the signs are, I'm factoring a negative out because if it's supposed to be odd, there's got to be a negative sign there. So I'm just, you know what I mean? Yeah. All right. Let's do the last one. Any guesses as to what this one's going to be? That would be the standard, like, well-designed lesson. We've done one of 3 examples. There's supposed to be one of each. There could be one of 3 things. Probably do one of each of the 3 as our 3 examples, right? All right. So I typed in 4x squared minus 3x plus 9. I hit graph. I see a little bit up here, but I'm not sure that's enough to really tell me what's going on. So I'm going to change my window a little bit. I need bigger y's to be able to see what's going on because it's all off my screen, like up here. So when I press window, I'm going to change the y max. I want to be able to see more y's up. So I'm going to change that from like 10 to 20 or something. There we go. Now what is this one? Neither. Why isn't it even? It kind of looks like an even one. Right, so the y-axis doesn't split it into 2 equal pieces. Everybody see that? That there looks like there's a little more of the graph on the right than there is on the left. That doesn't mean it means it's not even either. So this is a neither. Everybody's happy with what we're seeing? Okay. Okay. So to do a neither, what we need to show then, I think we're on H as our letter. We need to show that h of x is not, or h of negative x is not equal to h of x. And also, h of negative x is not equal to negative h of x. Right? We're showing that it's not even. And also that it's not odd. Everybody's happy there? Okay. So we'll start the same way. We'll do h of negative x. And just like all the previous ones, what that means is I'm going to plug negative x in for x's. So the 4 stays, then I have a negative x, then I have my squared, then my minus 3, and instead of an x, I have negative x. And then the plus 9 just stays plus 9 because there's no x attached to it, right? So starting it just like I have every other one, no big deal. I'm going to go ahead and simplify this. What is negative x squared equal to? Just x squared, right? So 4 times x squared is just 4x squared. What's negative 3 times negative x? 3x, so I'll have plus 3x. And then I have my plus 9. So at this stage of the game, I notice that this does not equal h of x, right? So I know that we're not even. Why doesn't it equal h of x? The signs on the 3x's are different, right? Even though everything else is the same, if there's one difference, that's enough to say they're not equal. So far, so good. Now, what I'm going to do is I'm going to factor a negative sign off. So when I do that, positive 4x squared becomes negative 4x squared. Positive 3x becomes negative 3x. And positive 9 becomes negative 9. And this is not equal to negative h of x, which would be negative 4x squared plus, well, let's write it in a factored way. And since that's true, we know it's not odd. And if we have not even and not odd,
Hey, Tommy.
we know it's neither. Everybody feel okay with the reasoning there and like the algebra that we did? Okay. Guess what? That's all of 8-5. Or I'm sorry, 1-5. At this point, you guys should be able to do problems 19 through 22. We're also today, though, going to look at section 1-6. That's another, probably about as long as that previous section was, not too bad. Still just scratching? You're good. I'm just going to check every once in a while if I look up and I see you. Section 1-6 is about asymptotes. Do you remember the term asymptote from last year in your Algebra 2 class? Depending on how far you got, I know some of us had, like one teacher all year that did a good job, and some of us had 3 teachers for the year who collectively were kind of all over the place. So I don't know how far everybody got, but we'll start off assuming that kind of like we'll do this all from scratch. But some of us might hear this stuff and say, oh, I remember this, which is good. If you don't, it's okay. We're doing it again right now. So we say an asymptote of a graph is a line that the graph approaches but never touches. These asymptotes can be horizontal or vertical. When we say approaches in mathematics, what we mean is the graph will get closer and closer to that line, but not necessarily get there. Notice that I have this little asterisk here on the word horizontal. And that's because we're going to be a little bit more flexible with the horizontal, what we call a horizontal asymptote. So for the sake of simplicity, we're going to refer to some horizontal lines as asymptotes, even though the graph might touch them, provided that at the ends of that horizontal line, the graph is doing that approaching but not touching. But it might cross in the middle. Everybody's okay with that idea? So let's look at an example just to make sure. So we'll look at a picture here. Actually, let's actually do it this way. I'll put the picture in and we'll draw some stuff in. So let's say we have this function here. So this is called a rational function. You might remember that term from last year in your Algebra 2 class. A rational function is just one polynomial divided by another polynomial. So I'm going to graph this now. To graph this one, I'm going to use this different software to do it. And I'm only doing this because I want to embed this image into the OneNote so I can draw on it. And it's just, I get a better picture doing that with this software than I do with the calculator software. If I were to graph this on the calculator, I would do it the same way. But I want to draw on the graph to kind of point some stuff out to you and talk about what we mean. That's why I'm using this software right now. This is called Graphmatica. It's a free download if you're interested. So if I look at this graph, it looks to me like I see what? 3 asymptotes. I see 2 vertical ones and 1 horizontal. So it looks like here at x equals -3, there's a vertical asymptote. Notice the graph gets closer and closer to that line, but doesn't ever seem like it's going to get there. Everybody see that? I see another vertical asymptote at what appears to be x equals 1. Again, as the graph gets closer and closer, but doesn't ever look like it's going to touch. Remember from your Algebra 1 course that we name a vertical line x equals and then the number. Because if I say, I'm talking about this line, every point on that line has the same x coordinate, right? All the points on that line start 1 comma something. So we name the line x equals 1 because all of the x's on that line are the same number, 1. And then I also see a horizontal asymptote, and that appears to be the line right here. Looks like y equals 1. And note, even though it appears that that graph is crossing, we still call that an asymptote because at the ends, we have that approaches but not crossing behavior, even if we get a cross in the middle. Still going to count those as asymptotes. Everybody okay with that? So just some vocabulary right now, right? Okay. So What if we wanted to use a table of values to confirm that the asymptotes that we saw above, x equals -3, x equals -1, and y equals 1, are indeed asymptotes? Let's talk about how to do that. So we'll do this kind of one at a time. We'll do it for x equals -1, and then we'll do it for x equals +1, and then we'll do it for y equals 1. Okay? So I'm going to make myself, an XY table. So I'm going to pick x values that are going to be getting progressively closer to -3. I'm going to start with numbers that are less than -3. So maybe I'll start with -3.1, and then -3.01, and -3.001. Notice each time I'm getting closer and closer to -3, but I'm staying on the left side of -3, right? The numbers that are less than -3. Now I'm going to do it from the other side. So maybe I start with -2.9, and then 2.99, and then -2.999. Again, each step I'm getting a little bit closer to -3, but all those values are from the right side of -3. Everybody feel good so far? How am I going to get the y values? I'm going to plug those numbers in for x into our equation up here. Now that stinks a little bit, right? Because that's a lot of typing into our calculator. Wouldn't it be nice if I could just tell the calculator the x value and just have it plug it in automatically for me? Guess what? The calculator can do that. You just have to know how to ask it. Let's show you, because it'll make these type of problems a whole lot simpler, right? All right. So I'm going to start by going to the y equals. So I'm pressing the y equals. I'm going to clear out anything that I might have had in there from previous problems. And then I'm going to type in this function into the y1 spot. So notice this one has the horizontal fraction bar in it. To type something with the horizontal fraction bar in, I think the easiest way to do it is to use a horizontal fraction bar on your calculator. To get that horizontal fraction bar, the easiest way to do that is press alpha, the green button, and then y equals, and choose the first option. That'll get you a horizontal fraction bar, so you don't have to muck around with a bunch of parentheses. That's nice. If you haven't seen that command before, you'll end up using it a whole bunch of times here, because I'm going to use it like almost every day we pull out the calculator at some points. And now I can type this into my calculator exactly like it looks like on my sheet of paper, which is awesome, and not have to muck around with a bunch of parentheses. If I did want to use the division symbol, I'd have to use a set of parentheses around the numerator, do the division, and then a set of parentheses around the denominator, and then make sure I didn't screw anything up with the parentheses opening and closing. It's just way easier to just type it the way it looks. That's what I like to do. Everybody cool? I'm going to do a quick check of the graph and make sure it matches the picture, just to make sure that I typed this in correctly, right? So I'll do zoom standard here because I changed my window before. But if I look at this, this is the same picture that I'm getting before. I can use my picture to identify my asymptotes. Let's see, -1, -2 looks like -3. And then looks like here at +1. And then here at +1. So I can use the graph to identify my asymptotes, what I'm looking for. Now let's worry about filling these values in, right? So what I'm going to do is I'm going to exit out to the main screen. So I'm going to press second and the mode button, which is right next door to the second button, to get me back to the main screen. And now I typed my function into the Y1 spot, right? So if I'm doing if I'm thinking about this as like a function notation, I want to do like Y1 of negative 1.3. So it'll go and like plug negative 1.3 in for all that stuff, right? Everybody's okay? That's what I want the calculator to do. So to get that Y1, I'm going to press the vars button, which is right here underneath the down arrow. Now I'm looking for Y1. Vars is short for variables, by the way. So I want the Y variables. So I'm going to move my cursor over so that I'm in the Y vars tab. And our calculator is going to be in function mode. So I'll press enter there. And ha! There it is, the Y1. So I'm going to do Y1 of negative 3.1. And then press enter. Woo! Now, Mr. Kulik, that was like a whole bunch of menus that you went through to get that Y1. Do I have to do that every single time? No, man, watch this. If I press second and enter, it'll give me the last thing I just typed in, and I can just go back and edit it, and then press enter again. I don't have to go through all those menus every single time. And then I can just press second and enter, and go back and edit what I typed in last. And there we go. Now we're cooking with gas, Mr. Kulik. I like this. Isn't that way nicer than trying to plug that stuff into the function on my calculator? Yeah, man. Oh, biscuits. I'm just trying to grab that. All right, there we go. Let's start recording some of this stuff that I just typed in. So negative 656, negative 7406, negative 749.06. If I look at these three values, notice each time I get a little bit closer to negative 3, the y value is getting a lot smaller, right? Everybody see that? We go from negative 656 to negative 7406 to negative 749.06. So what are these doing? The y here is heading towards negative infinity, right? Let's look at what happens when we approach negative 3 from the other side. So again, I'm going to just do second enter. I'm just going to go over and edit this to be 29, or 2.9, negative 2.9. And then we're going to do the same thing. Just do some second enters. So I get 844, 7594, and 750.94. If I look here, the y's are heading towards positive infinity. You take these together, we can say we have a vertical asymptote. I'm gonna, oops. Get that out of there. So far, so good? All right. Let's do the same thing now for this one, x equals 1. So we'll start by picking some values of x that are smaller than 1 and getting progressively closer to 1 each time. So maybe 0.9, 0.99, and then 0.999. And then we'll do some values that are a little bit bigger than 1. And again, progressively getting closer to 1. So far, so good. Okay. Now it's calculator time. So again, I'm just going to do second and enter and just edit what I have here. And then we'll just do the other 3. While I'm doing this, do you guys have questions about why we're doing this, or what this is showing, or how to do this, anything like that? This is okay though? I mean, it's pretty straightforward, right? The calculator makes it pretty easy to do this. Back when I was a kid and we had to do this all by hand, this was a pain in the tuchus. But with these modern calculators, boy, it makes it a lot easier. Put the y equals 1 down here. Now here things are changing a little bit, right? Because my horizontal asymptote isn't in an x location, right? The x is getting bigger and bigger and bigger, smaller and smaller and smaller, but the y is kind of staying the same. So here we have to be a little bit different for the horizontal. So I'm going to start by looking at progressively smaller and smaller y's. So like maybe -10, -100, -1,000. And then progressively bigger and bigger x's, so 10, 100, and 1,000. And what I'm hoping to see is that when the y's change, they're getting closer and closer to 1, right? So again, just second enter. And I can edit that down. Oh, boogers. What is happening now? It's giving me a fraction. What do I really want here? Decimal. So this is what I'm going to do. I'm going to press second enter, and then after this, I'm going to press the math button and choose the DEC command. That means give me a decimal. That tells the calculator to give my answer as a decimal. And then I'll just do it again. Now here, if I try to edit this, I have to be a little bit careful because it'll overwrite what's on there, and I want to save that DEC command so I don't have to go in the menu and get it every time. If I press second and then the delete key, above that is INS, that's short for insert. So if I do second and then the delete key, notice my cursor changes to be flashing clear rather than flashing black. So now I can just add in a 0 without overwriting anything. And what do you notice here? If I add another 0 in, so I get -1,000, we're getting closer and closer to 1, just like we hoped, right? Now we'll do the same thing. I'm going to do it this way, though, and start from the bottom up so I don't have as much... I don't have to do the insert command. I can just delete one digit off of it. Okay, so when we're doing this, if the y's are heading to an infinity, that indicates us a vertical asymptote. If the y's are heading to a finite value, that indicates for us a horizontal asymptote. Yes, sir.
Did you press the cursor flash here?
So I did second and then the delete key. Above the delete key is INS, that's short for insert. So that'll allow you to insert values without deleting anything, which is a good one to know, because boy, that can save you a lot of typing on your calculator, right? Alondra. This is just to confirm what we're seeing graphically, right? This is just another way of checking. So like on the homework or a test or whatever, if I ask you to provide a table to support your answer, this is what you would do. Does that make sense? So it's just confirming or supporting what we're seeing visually when we look at the picture. Another way of doing it. Or I could give you a table of values and ask you to identify the asymptotes by looking at the points, right? Like I could do it that way. Does that make sense? Nick, you had a hand? You're good? Guess what? That's all we needed from 1.6 also. So just that one idea. You guys should now be able to do 23 and 24. We're going to stop here today because, quite frankly, that was kind of a lot of stuff we just did. And I have something else to show you. So I've also, in addition to your problem set for this chapter, I've made a Delta Math assignment. So I think that most of us have done Delta Math last year a little bit. Typically we'll get like one or so Delta Math assignments for a chapter. So here I have, we have 6 different kinds of problems. You have to do 4 correct from each type. So the first problems are just deciding if something is a function or not. Second set is writing things in interval notation. Third set is like figuring out the domain for like a story problem where there's a real world, the variables mean something. There's a horizontal and vertical line test. We haven't talked about the horizontal line test, so you could skip this for now. And then these inverses. We haven't talked about inverses yet. You could skip those for now. We'll talk about inverses in the next section. But we have enough to do some of these, and rather than just like dumping it all at once, I'll give you a heads up and just let you pick away at stuff. The Delta Math is set up so there is no penalties for wrong answers. So you won't get locked out. This is for completion only. You don't have to, I'm not worried about how many tries it takes you to get your right answers. You do not need to get 4 in a row. You just need to get 4 total correct answers in each category, and then it should move you on to the next category. Everybody feel okay?
Yeah.
Okay. That'll be due on Sunday also, so you have, the week or so to work on it. And if it becomes clear that like we're just not ready to have this done by Sunday, we can always move it. But we'll talk about that again on Thursday. Everybody feel okay, Lucas? Certainly. Okay, what do we got? Like 15 minutes or so, 10, 15 minutes left of class. I would get something out and start banging away maybe at your Delta Math or these next 5 or 6 problems that we assigned today for your problem set.
So do you want us to like prove it's like why it's odd?
Yeah, in the homework. Yeah. So on the problems where it asks you to determine if it's odd or even, I would think about it more as show. So like do the proof kind of thing would be good. Yes. Good practice. Oh.